Hello and welcome back. So for this video here, we're going to be looking at our third and final example of related rates. And for this particular problem, we're going to have sand that's being dumped from a conveyor belt onto a pile, and that pile is going to be approximately made by a right cone. It's not perfect, but again, it's a good estimate of what's really happening in this example here. So when you draw a right cone, you want to make sure that you start with a triangle and then put a round base on it. And again, we're going to have sand that's being dumped onto our cone. The cone is going to have a diameter and, more importantly for this problem, a radius. And it's going to have a height that is increasing as we pile more sand on top of it. So we're going to let the vertical height of the cone be h of t, and we're going to let r of t be the radius of the cone. The formula for the volume is going to be v, which we're going to write as v of t, is the constant pi over 3 times the radius of our cone squared times the height of the cone. And in this problem, we want to find the rate of change of the radius at a moment in time. So the first thing we want to do is go through and take derivatives and be very, very careful in this problem, because you will notice that you're going to have a chain rule and product rule as part of the derivative process. So when we go through and find our derivative, we're going to have v prime, which is the derivative. And don't forget, we are taking the derivative with respect to t here, right? So it is v prime of t, but we're going to write it as just v prime. And that pi over 3 is a multiplied constant, which will be times the entire derivative. And now in using our product rule, we're going to have the derivative of the first. So that's going to be 2 times r to the first power times r prime, which is going to be the derivative of r. And that's multiplied times the second function h. So again, that's the derivative of the first times the second. And then we're going to add on the first, which is r squared, times the derivative of the second, which is just h prime. So that is the symbolic answer for our rates of change equation. The next thing we want to do is we have to make a decision between substituting in values early and working with numerical values, which could get into fractions and decimals and rounding, or we could just work the problem out symbolically and then at the end of the problem evaluate our expression given the numbers in the problem. I prefer to symbolically solve, so I'm going to actually isolate this r prime. And then at the end, again, just substitute everything in and calculate out watching our units. So first thing to do to isolate this r prime is to multiply both sides by the reciprocal, 3 over pi. So we're going to have 3 over pi. I said 3 over pi. 3 over pi times v prime is equal to 2r prime h plus r squared h prime. The next step, we will subtract r squared h prime from both sides. So we're going to have 2r prime h is the 3 over pi v prime minus r squared h prime. And then finally, we can divide both sides of this equation by 2rh. And we now have an expression for the rate of change of the radius. R prime is the 3 divided by pi v prime minus r squared h prime divided by 2rh. The next thing to do is now extract all of these values from the original problem. So r prime will be equal to 3 over pi times the value of the rate of change of the volume. If we go back to the problem that was given to us as 4,000 pi cubic feet per minute. So we'll substitute that in. That's 4,000 pi cubic feet per minute. And now we have to subtract away the radius squared times h prime. The radius in the problem wasn't explicitly given. The radius was given to us in code by telling us that the diameter is 30 feet. So if the diameter is 30 feet, our radius must be half of that, which is 15 feet. So I'm going to substitute in 15 feet in place of my radius. And now we need to get the rate of change of the height. And in the problem, it tells us that the rate of change of the height is going to be 3 feet per minute. And again, please make sure you're putting your units on these. So again, that's 3 feet per minute. And again, that's all divided by our 2 times our 15-foot radius and a height that was given to us as, where did it go? 40 feet. All right, so at this point, this is all just careful evaluation with our calculator. Again, we've got the 3 over pi times the 4,000 pi cubic feet per minute. We can obviously cancel out those pi's, and that'll just be 12,000. Back here, when we calculate, we're going to have 15 squared times 3, which will make 675 units on this will be cubic feet per minute as well, because we have square feet times another unit of feet. And then down below, we've got 2 times 15 times 40. That's going to be 1,200 square feet. All right, so we now have our R prime, which is going to be 3 times 4,000, which is 12,000 cubic feet per minute, minus 675 cubic feet per minute, divided by our 1,200 cubic feet. And once again, it's always important to look for road signs along the way that we're doing things right. You'll notice that we are subtracting the same units in our numerator, which is wonderful, because if they were not the same, we'd have a big mess on our hands. But they are the same, and you can actually subtract away those two numbers and get R prime is equal to 11,325 cubic feet per minute divided by our 1,200 square feet. You will notice that the units will work out perfectly, because if I take cubic feet and divide by square feet, I just get linear feet. And if I divide this out, I'm going to get the decimal 9.4375. And again, those are going to be feet per minute, which makes sense for a rate of change of a radius. So our radius is growing at roughly 9.4 feet per minute, as our height is increasing at 3 feet per minute, and we have our volume changing at 4,000 cubic feet per minute. So it's pretty obvious that our radius of our pile is getting bigger faster, so this is probably some sand that disperses pretty widely as you pour it. But again, that is the entire process of the related rates. And again, extremely important to make sure that you always express your functions of time so that you can capture the correct derivatives. And again, I prefer to always go through and symbolically solve for the unknown rate and then just substitute at the end, rather than trying to crunch out the calculations with the numbers from the start of the problem. But again, different styles for how to solve this problem. And just make sure, of course, your units make sense as a check, and make sure you're careful with any signs of units that are increasing or decreasing as well.